April 2nd, 2010, the Tesoro refinery in Anacortes, Washington. A nearly 40-year-old heat exchanger violently ruptures, causing an explosion and fire that kills 7 workers, the largest loss of life at a U.S. refinery since 2005. The Chemical Safety Board launched an investigation and determined that the heat exchanger catastrophically failed due to long-term damage from what is known as high-temperature hydrogen attack. The CSB's final report into the accident was unanimously approved at a public meeting in Anacortes on May 1, 2014.
The CSB is seriously concerned by the number of deadly refinery accidents in recent years. We have concluded that extensive improvement must be made in how refineries are regulated at the state and federal levels.
The Tesoro refinery in Anacortes is an 800-acre facility located approximately 70 miles northwest of Seattle. The refinery produces a variety of products, including gasoline, diesel, jet fuel, and asphalt. Within the refinery's naphtha hydrotreater unit, raw naphtha, a light component of crude oil, is treated to remove nitrogen, sulfur, and oxygen impurities. Before entering the unit's reactor, the raw naphtha and hydrogen are preheated inside pressure vessels called heat exchangers. The unit contains 2 banks of 3 heat exchangers supported by a 3-level steel structure. Each heat exchanger consists of a bundle of tubes inside a steel shell. Hot fluid exiting the reactor flows through the heat exchanger shell, while cool fluid headed for the reactor flows inside the tubes. Heat is exchanged through the walls of the tubes. Every 6 months, the heat exchangers are taken offline to be cleaned because of fouling, a common occurrence when operating heat exchangers in this type of service. As the raw naphtha is heated, a scale-like material forms and deposits onto the inside of the tubes, hindering the transfer of heat in the exchangers. On March 28, 2010, 1 bank of heat exchangers was taken offline and disassembled for cleaning, while the other bank remained in service. This allowed the unit to continue to operate. By mid-afternoon on April 1st, the cleaning was complete, and operators initiated the startup of the offline bank of heat exchangers. The procedure required an inside board operator monitoring the control console and 1 outside operator opening and closing large manually operated valves. But the heat exchangers had a history of developing leaks during startup, something that refinery personnel had come to see as normal. Additional operators from other nearby units were called upon to assist with the startup, including mitigation of potential leaks. By 10:30 p.m., the outside operator was joined by 6 workers from other units within the refinery. The 7 workers were located around the heat exchangers, where startup activities continued past midnight. But unknown to the workers, the steel shells of the middle vessels in both banks of heat exchangers had been severely weakened due to cracking caused by high-temperature hydrogen attack. This occurs when tiny hydrogen atoms diffuse into steel at a high temperature, then react with carbon in the steel to form methane gas. The larger methane molecules, unable to diffuse out of the steel, accumulate, stressing the steel and over time causing fissures. In both of the middle heat exchangers, the fissures grew and connected to form large internal cracks. One such crack was 48 inches long and extended more than 1/3 of the way through the vessel's 1-inch thick shell. Shortly after midnight, the temperature of the fluid exiting the tubes of the online bank of exchangers increased about 75 degrees over the span of 3 minutes, a temperature increase that was typical and observed in previous startups. But the middle heat exchanger was so severely weakened from high-temperature hydrogen attack that it likely could not withstand the stress caused by the rapid temperature increase. At 12:35 a.m., employees working at a nearby process unit heard a loud hissing noise when vapor began to leak as the heat exchanger cracked at its weakest point. Seconds later, the exchanger violently ruptured. Hot hydrogen and naphtha vapor rapidly vented from the exchanger and spontaneously ignited upon contact with air, resulting in a massive fire that consumed the heat exchanger structure. 3 of the 7 operators died at the scene. The other 4 operators were transported to local burn centers with severe injuries. 2 died within hours. The other 2 succumbed within days.
High-temperature hydrogen attack, or HTHA, is a common hazard that has long been known within the petrochemical industry. However, Tesoro engineers and corrosion experts did not believe it could occur within the heat exchanger that ultimately failed.
The CSB learned that, like other companies, Tesoro relied on data published by the American Petroleum Institute called the Nelson curves to predict the susceptibility of the carbon steel heat exchangers to HTHA damage. They take into account process temperature, the amount of pressure contributed by hydrogen, and the kinds of materials used in constructing the equipment. Above each Nelson curve, HTHA was thought to be possible. Below each curve, HTHA was not predicted to occur. But after conducting detailed process simulations, the CSB concluded that the portion of the heat exchanger that ruptured actually had operated below the curve for carbon steel, in a zone that industry guidance considered safe. And the CSB has learned of at least 8 other refinery accidents where HTHA reportedly occurred below the carbon steel Nelson curve. As a result, the CSB determined that the carbon steel Nelson curve is inaccurate and cannot be trusted to predict the occurrence of high-temperature hydrogen attack. Furthermore, the CSB found that Tesoro did not measure actual operating temperatures and pressures in the exchanger that failed. Instead, corrosion experts hired by Tesoro relied on design operating conditions to predict whether HTHA would occur based on the Nelson curve. And the CSB's process simulations indicated that when the exchangers were fouled, the actual temperatures were likely much higher than design conditions.
Had Tesoro used actual process conditions when determining HTHA susceptibility of the heat exchangers, their internal policies would have required the heat exchangers to be inspected for HTHA. However, we note that inspection for HTHA is not very reliable.
That is because damage to equipment may be microscopic or limited to small areas, but still be significant enough to cause catastrophic failure.
The best way to prevent HTHA is by using inherently safer materials of construction that are much more resistant to high-temperature hydrogen attack. For example, industry has already identified steels with higher percentages of chromium and molybdenum that are much more resistant to HTHA.
The CSB recommended that the American Petroleum Institute revise its standards to prohibit the use of carbon steel equipment in HTHA-susceptible service and to require verification of actual operating conditions.
The safety culture of a company can have a huge influence on the actions it takes to prevent accidents. During our investigation of this accident, we discovered several instances where Tesoro's safety culture was lacking.
The CSB learned that the heat exchangers had a history of leaks during startup, creating hazardous conditions for personnel working nearby. However, the CSB found that although Tesoro took some corrective actions, it never adequately fixed the leaks. Instead, Tesoro treated the leaks and fires as normal occurrences and regularly allowed additional personnel to be present during startup to mitigate the hazards. On the night of the incident, 2 more leaks were reported during the exchanger startup. And the CSB found that the complexity of the startup procedure typically required more than just the one outside operator. Yet operating procedures were not updated to account for the role of additional personnel during the hazardous non-routine work.
These additional operators were exposed to a serious risk.
7 workers, including 5 additional operators from other refinery units, were supporting the startup of the heat exchangers on the night of April 2nd, 2010. All were fatally injured.
The CSB found that if Tesoro had a strong safety culture, it would have addressed the ongoing leaks and defined a reasonable number of essential personnel for the startup activity. Had Tesoro done these things, we concluded that fewer workers would have been present on the night of the accident, and lives would have been spared.
The CSB recommended that Tesoro implement a process safety culture program that would assess and continually improve safety at the Anacortes refinery.
Our Tesoro findings are all too similar to those of other CSB refinery investigations.
The CSB has found these similarities include weaknesses in industry standards for safeguarding equipment, a deficient refinery safety culture, and a regulatory system in need of reform. Under the existing state and federal regulatory systems, there is no requirement to reduce risks to a specific target. The regulations predominantly require only the completion of activities or tasks, such as hazard analyses, but the regulations do not mandate actual risk reduction or continuous safety improvement.
The CSB believes the goal should always be to reduce the risk of major accidents to as low as reasonably practicable, a concept known in the industry as ALARP.
To reduce accident risks, the CSB made the following recommendation to the U.S. Environmental Protection Agency. Revise rules under the Clean Air Act to require that facilities analyze and use inherently safer technologies to the greatest extent feasible. Use the hierarchy of controls, with safe design at the top of the hierarchy, to reduce process hazards. Tragically, Tesoro only opted to install an exchanger made of a safer HTHA-resistant alloy after the disastrous explosion that cost 7 workers their lives. And the new design eliminated the risky step of switching between the parallel banks of heat exchangers. Until the EPA promulgates a regulation, the CSB recommends the EPA use its authority under the Clean Air Act's General Duty Clause to promote wider use of inherently safer design. The CSB also recommended that the governor and legislature of the state of Washington significantly strengthen the oversight of refineries. Specifically, the board called on the state to require refineries to conduct more comprehensive hazard analyses and damage mechanism reviews, document the effectiveness of process safeguards, and increase the role for worker representatives in process safety management. And these more rigorous company safety reviews should be examined by technically competent regulators. The CSB determined such regulatory changes would help prevent future accidents like the tragedy at Tesoro, where many opportunities to identify and reduce hazards were overlooked.
7 lives were lost at Tesoro. It should not have happened. Companies, workers, and communities would all benefit from a more rigorous regulatory system that is focused on continuously lowering risks.
For more information on the CSB's Tesoro investigation, please visit csb.gov.